guess we're on. All right, so we just saw osmosis or osmotic pressure. We saw that if we increase the solute concentration, we increase the osmotic pressure, we increase the osmolarity. The next of the two that we're going to look at, we're going to look at them both at the same time, are freezing point depression, boiling point elevation. Depression, elevation. Freezing point depression, boiling point elevation. Freezing point depression, boiling point elevation. I hope you say it over and over so you remember that when you add solute concentration to a solution, the freezing point drops, and if you add more solutes to a solution, the boiling point elevates. The equation for describing it is right here. It's not an equation you have to memorize. I will not have you memorize these two equations. However, what I want you to recognize with them is that the change in the freezing point, looking at freezing point depression first, is equal to I is the number of particles, times a constant. Notice the negative sign means that the freezing point is dropping, moles per kilogram of water. So it's just a unit. It's just a constant. And then this is the moles, and referring to moles, the moles of the solute per kilogram of water. So as the mole concentration of solute increases, the freezing point decreases because of the negative sign. Looking at the boiling point elevation equation, it looks the same. Everything about it's the same, except the constant is different. And when you see this, you notice how this is a larger negative value than that is a positive value. So freezing point depresses more for a given amount of solute than you get for boiling point elevation. Looking at some of these, ethylene glycol, a non-electrolyte that you can put into your car that is an antifreeze. So if you put 1 mole of it in, 1 mole of ethylene glycol, which breaks into 1 mole, since it's a non-electrolyte, it doesn't break apart in the particles, the freezing point would drop by 0.86 degrees Celsius. So pure water is at 0 degrees Celsius. You put in 1 mole of ethylene glycol, the freezing point drops to 0.86 degrees Celsius, negative 0.86 degrees Celsius. And the boiling point would elevate to 100.52, so it went up just 0.52 degrees Celsius. If you took sodium chloride, 1 mole of sodium chloride, and you threw that into a solution, because it's a strong electrolyte, it breaks into particles. You get 2 particles, so you have 2 moles of particles. The freezing point would drop to minus 3.25 degrees Celsius, and the boiling point would rise to 101.04. If you took 1 mole of calcium chloride breaks into 3 particles, so you have 3 moles, another strong electrolyte. The freezing point would drop to minus 5.58 degrees Celsius, and the boiling point would rise to 101.56. So you can notice that this is not as large of an increase as this is a decrease. Some important applications of this colligative property. So we can use sodium chloride or calcium chloride to melt snow. So when you throw salt onto the roadways, what you're doing is you're dropping the freezing point, which turns it to water, which makes it more easily able to evaporate, melts the snow, and we can get the tires onto the road. Ethylene glycol as an antifreeze for radiators. One of the interesting things that we can do when we think about osmolarity doesn't directly apply to freezing point depression or boiling point elevation, but we can apply that idea to it. So I'm going to put up the slide here, and while I'm doing it, you can pause the video, and I'd like you to try to calculate the osmolarity of all 4 of these. So pause the video as I put the slide up, and you calculate the osmolarity of these. If you really want a good exercise in this, after you calculate these, determine which solution or solutions will have the lowest freezing point and which solutions will have the highest freezing point. So I'm getting a little tricky here, but see if you can't figure that out. So you're on pause, I'm on putting the slide. All right. You've unpaused. I'm hoping you paused. My daughter's laughing at me, which means you didn't pause. And I want you to calculate the osmolarity of each one of these. Now what you have to do is you have to think about the number of particles you're going to get. So this is sodium carbonate. Sodium carbonate breaks down. You're going to get 2 sodiums and 1 carbonate. So I is going to equal 3 here. So with I equal to 3 times the 0.1, your osmolarity here is 0.3 osmolar. This is sodium bicarbonate, the same thing as baking soda. If you look here, you get a sodium off of it, and you get the bicarbonate ion off of it. And so in this case, you're going to have I is equal to 2, and so times the 0.1, you're going to have a 0.2 osmolar solution. Over on this side, dextrose. Dextrose, you remember, is the same thing as glucose. So I is equal to 1. It's a non-electrolyte. It doesn't break apart. And so here you're going to have a 0.25 osmolar solution. And then here, looking at this one, this is sodium phosphate. You're going to get 3 sodiums off of it and 1 phosphate. So 3 sodiums plus 1 phosphate, I is equal to 4. And so 4 times the 0.05, you're going to end up with a 0.20 osmolar solution. Now, if we were looking at water flows, we could just look at these. But I can tell you that we can use this to estimate very accurately what would happen to the freezing point and what would happen to boiling point, which was not in this problem. So freezing point depression, boiling point elevation refer to an increased number of solution or solute particles. Osmolarity tells us that. It tells us how many solute particles are there. So looking at these, which one of these will have the lowest freezing point, or what solutions? It turns out the lowest freezing point is going to be by A, solution A. And the reason that it's solution A is because it is 0.3 osmolar, so it's the most solute particles in there. So it's going to drop it. That's going to drop it the greatest. Now, which of these solutions will have the highest freezing point? Well, in pure water, if you had pure water, the highest freezing point would be 0 degrees Celsius. So you can't go any higher than that. But the instant you start to put stuff in, the freezing point drops. So which one of these puts the least number of particles in there? The least number of particles come from B and D. Both of these are only putting in 0.2 osmolar worth of particles, so they will have the highest freezing point. The highest, remember, possibly could be with no particles would be 0 degrees Celsius.